This is the flip portion for logarithmic functions. So logarithms and exponential functions are inverse functions of one another. And remember that inverse functions graphically are symmetric about the y equals x line. So if you look carefully at this graph, you'll see that the exponential function, e to the x, and the log, and I know it's log base b, but I'm just using natural logarithms for now, ln of x is symmetric about the y equals x line. So if you were to fold it along that line, the two pieces would fall on top of one another. So a logarithmic function in general form is y equals log base b of x. But a log is nothing but a power. So it's a power or an exponent. So whenever you see a log function, what you should be asking yourself is what power does b need to be raised to get x? That's the question you want to ask yourself. So if I gave you the example log base 2 of 8 equals something. So the question that you're asking is what power does 2 need to be raised? So what power does 2 need to be raised to get 8? And of course, the answer to that question is 3. So that is why logarithms are a power, because 2 to the third is equal to 8. So there's your power, right there, 3. So a couple things graphically that I want to point out here is that as b gets closer, as b increases, the graph itself gets closer and closer to the x-axis. So as, I don't know if there's a lot of room here. Oh, I can't scroll. Alright, let me just try and point it out. It's hard to see. I'm not sure if you can see this on the video. But as b gets bigger and bigger, so here b is 2, b is e, b is 3, and b is 10. So as b increases, the function itself is going to get closer and closer and closer to the x-axis. So the log base e, pointing that out, which is often written and what you're most familiar with is ln of x. So log base e is between 2 and 3. And that makes sense because what is e? E is just an irrational number that's 2.7, right? 8. And indeed, that is between 2 and 3. All right. So from here, I think I want to just do an example working with logarithms. Actually, you know what? Let's continue on with a little bit of log properties. So this is the next chart from the packet for 1.3. I just want to do a review of the rules for logarithms. Again, the domain for logarithms is 0 to infinity. Right? X can't go negative. And the range is all reals. So these are just some properties of logarithms. And again, this is an important inverse relationship. When we do equation solving, we'll be employing this relationship. The b raised to the log base b of x is simply x, and the inverse of that is that log base b of b to the x is also x. So you'll see that in action in an example. And these are just the refresher of the rules. Remember, when you argument to the log function is a multiplication, You convert it to addition. So let me put it this way. Multiplication converts to addition for logs. Division converts to subtraction. And again, a power is going to reduce down to a constant multiplier. And just another property log. Base b of b is equal to 1, because what is the question that you're going to ask yourself? What do you need to raise b to get b? And the answer is 1. The last concept on this chart is the change of base rules. All right, change of base rules, and I'll show an example of them. When are they typically used? They're used for conversions. Because your calculator, if you have a TI, uses base 10. So you have to know how to convert. And the one that you will use the most is right here. And this is the one I'll be concentrating on. The log base b of x is equal to ln of x divided by ln of b. That's the primary one that I'm going to be using, which coincides with this property. B to the x is the equivalent to e to the x ln of b. And if you and that's for all x. So that's the bases that I'll be concentrating on primarily. So let's do a quick example with I want to do an equation solving example for you, and then have you solve one in class. So let's do a simple one, I think, first, and then we'll do one in class. So I'm going to pause here and come up with something. Okay, I just worked up a quick example. Solve the equation for x, and you're given an exponential function equals 12. So the key here is to unlock the exponent. And to unlock the exponent, you need to take the natural log of both sides, right? Because this expression is going to unlock the exponent, because ln and e are inverses of one another. So this is equal to 2x minus 4 on the left-hand side, and the right-hand side is equal to ln of 12, which is simply a number that you could put into your calculator. Now continue to solve this equation. Get rid of the negative 4, so add a 4 to both sides, and then divide by 2. So you're left with x is equal to ln of 12 plus 4 over 2. Now you can enter this expression into your calculator, since your calculator knows how to do natural logarithms, and you can get a decimal value. But the most accurate thing to do is to just leave it in this form. Okay, so that's an example of using the inverse property of logarithms, and specifically using it to solve the equation for x.